Perfect. All right. So I'm Barry. I'm doing the speaking. Again, I'm a professor of computer science at the University of Richmond in Richmond, Virginia. Some photos there. Also here today is Vadim Kudlay, who's an undergraduate junior in computer science and mathematics at the University of Richmond, and then Larry Leemis, professor of mathematics at William and Mary. And so what we're going to talk about is a package that we've written to help out with simulation education, and that package is called SymEd. So a little bit of outline. I just want to talk about what SymEd is. I want to talk about what it's not. And then we're going to spend some live, most of the time doing some live demos by Vadim to show off some of the really great work that he's done in his undergraduate research. So first off, what is SymEd? It's a package that's available on the CRAN or CRAN, however you prefer to pronounce it. It contains various functions that can be used in teaching a simulation course. And Larry and I have used this in upper level undergraduate courses as well as intro graduate level courses. It contains a whole lot of functions. Step on down, Vadim. It contains a whole lot of functions for things like simple Monte Carlo simulations, some functions to implement single server queuing, multiple server queuing. We have our own versions of random variate generation that I'll talk about in a minute. So a la things like rnorm and runif and rexp, we have our own versions that include streams, and then a lot of really nice visualization and animation routines that Vadim has written. What SymEd is not, it's not intended to be a general purpose simulation package. There are already things that exist out there like Simmer. It is also not a visualization package for arbitrary simulation models. Instead, it's very catered to the kind of stuff that we're doing in this simulation education vein. The intent is to allow students to really focus on intuition rather than coding and theory details. And so what we'll do now at this point is we'll just let Vadim jump over into R and we'll do some live demos. So Vadim should have pulled up there already an R session, just console in the terminal, where he has the SymEd library loaded. So as I mentioned, we have our own variate generator function. So I just want to briefly show you one example of that. And so Vadim, if you could do the vnorm. So what Vadim is to generate 3 normal random variates with mean 10 and standard deviation 2.5, and using a stream of 1. I won't go into all the details, but essentially for rnorm, we have vnorm. For runif, we have vunif, and so forth. And we're allowing for streams, which essentially means for stochastic components, we can ensure that each stochastic component is independent, which is really important in simulation. So we have capabilities like that. We also have a function called SSQ and another function called MSQ. So let's just show an example of the SSQ function. So what we've done here is we have implemented an event-driven approach for a single server queue model. And so students who are new to this can run and start to experiment with the simulation model in a way that they don't have to worry about details of the code or anything else. So here's an example where Vadim ran this SSQ with default inputs and just 100 customers. So you can see it will spit out output like the average weight for a customer, the average number in the queue across time. So we can do particular things like that. The nice thing about it, though, is even though that's already implemented, students can then write their own simple functions. So this implements by default an MM1 queue, which means exponential inter-arrivals and exponential service times. But what Vadim is going to do now is to write his own service function that will still be exponential, but with a faster rate than the default. And so now if he just pulls back an example here where we're going to run SSQ with the same 100 customers and give it a particular initial seed, but pass in his service function. What I want you to notice is that the average weight for customers here is 2.42 units of time. If he were to go back and run that same thing, but take out the, do it with the same seed, Vadim, so just remove the seed 8675309, which we all know is our favorite seed, and you look at the average weight, this one has slower service time, so you can compare that 3.96 to the 2.42 that was before. So the whole idea here is that students can really quickly get involved in these things by just making some simple implementations. So it's really flexible in the sense that students can pretty easily plug in and experiment with these different models. So those are just some examples of existing kind of text-based ones. Those exist in a package that's already available on the CRAN. So what Vadim has been working on has been really to build some really nice visualization and animations that we're going to include as part of this package, but is not yet available on the Crayon. So the first thing that we'll show is an animation or visualization of a Lehmer random number generator. So this is a really nice example of a random number generator that you can present to students so they can quickly understand. It uses a simple multiplicative equation with modulus. And so Vadim, if you go ahead and pull up Lehmer, what we can talk about here in a visual kind of way is that now what we can do is we can play around with the various parameters, A, which is known as the multiplier, M, which is the modulus, and the initial seed here is 1. And so what we tell our students is that this creates, based on the choice of parameters, a virtual circle of random numbers. So that initial seed of 1 gets plugged into the equation on the left, right, producing the next integer 13. And so then to get the uniform 0, 1, we would divide that by the current m, and so it gives us a uniform 0, 1 of 0.419, and you can see that appear on that graph at the bottom of where the uniform 0, 1s are being plotted as that blue dot. The way the generator then works, it remembers its state, so that 13 will then get plugged in. So Vadim's going to step to the next one here. The 13 gets plugged in, producing the next integer in that sequence, 14, which when we divide it by m gives us the next uniform 0, 1.452. So if Vadim keeps stepping around in this way, you'll see that these various random numbers are getting created. And each time that integer is divided by m, it produces another uniform 0, 1. So at some point, Vadim is going to come all the way back, and eventually we will start back at the initial seed. You'll see that it appears down at the bottom as well as a red dot. So what that means is we have now exhausted the really small period for this particular generator. This is not one you would use in practice, but it's good examples. And so if he keeps going again, what we do is we've then exhausted the period and we start drawing those random numbers again in exactly the same sequence. So we can talk a lot about this Lehmer generator. We can play around with different values of A and let students consider different aspects of that, or different values of M and so forth. And so that's an example of the Lehmer approach that he's used. So that's one of his visualizations. The next thing that we want to show are some examples of visualizing how to generate particular random variates. So this is something that we'll often talk about in a simulation course. And so what we're going to do here is visualize how it is that we've already shown how we can generate uniform 0, 1s. We want to show how we take those uniform 0, 1s and, for example, produce normals. So what Vadim is going to do right here is he's going to run a visualization routine that we call inorm. And similar to, you know, you have R norm, D norm, Q norm, P norm, and for various distributions as well. So we've just added I for inversion. And so this will give us a visualization. So what's going to happen here is this is going to show 10 generations, the generation of 10 different normal random numbers. So what's happening here is in that top row on the left axis, the vertical axis, we're generating one of the uniform 0, 1s using V unit, right? Our version of R unit. What then happens is to invert, we essentially map it back across that CDF corresponding to a normal with mean 10, standard deviation 2.5, and it produces the sequence of random variates, normal random variates, which are the dots on the bottom. So, right, so those are our 10 normal random variates. The middle row shows the histogram that's produced from those. And you can see that because we can talk about things like natural sampling variability and why those 10 don't produce a really nice, smooth, normal-looking histogram. And then the bottom row shows the empirical cumulative distribution function relative to the population as well. And so we can talk about those sorts of things. So you can, Vadim show them an example here where we're going to crank up the number to 100 with faster. And so you can see how the histogram is updating itself in the middle there as we go along. And so we also try to clean it up there if we get too many so that we're showing quantiles rather than every single dotted line across. But what we have in that same picture across the horizontal at the top are those 100 normal random variates, the ones on the horizontal. those, nope, across the horizontal there. And so those correspond to the variates that you see over in the terminal that have been generated. And you can see there how we get, you know, a little better looking histogram, but again, allows us to talk about things like sampling variability with that hole there between 6 and 7. Why does that happen? It's not anything bad, it's just natural sampling variability. And on the bottom, you can see how that the empirical CDF is fitting more closely, even though it's still a little noisy. So it gives us a lot of really easy to use ways that we can discuss these things with students. Okay, so we have those for normal, for exponential, for all of those different kinds of distributions. And so you can use them also for discrete distributions. Another example that we have that Vadim has implemented is a function that's called acceptance rejection sample. So as an example, the beta is a particularly ornery distribution that you want to generate variates from. So for example, uniform is pretty easy to generate from because it's a straight inversion, nice closed form expression. If you want to generate from normals, there are numerical approximation methods that you use. And one of the ways that you can generate from a beta is to use an acceptance rejection approach. And so we're gonna show an example of that right now. So this is a function, a visualization function that Vadim has written called AR sample. By default, it uses a beta 3.2, I think. Is that right, Vadim?
Yep, that's correct.
Yep. So the green line there in the middle row is the beta 3.2. So the way that the acceptance rejection would work here, and what we try to stress to our students, is we start out by generating a first uniform 0.1. That's at the very top in the yellow, and it gives us a 0.87. That tells us where we're going to fall on that horizontal. What we then do is to generate a uniform between 0 and the red line, which is what's known as the majorizing function there. And so what that would give us is a value of 1.12 in this particular case. If that value falls below the green line that we're trying to draw from, we accept, as we've done here, and it will appear in the histogram to the bottom. Not a very interesting histogram because it only has one data point right now. If it were above the green line, then we would show a red X and reject. So Vadim is going to step through a few here. So the next one here, you can see, so there's one where we had the uniform 0.1 drawn was 0.09, tells us where we fall on the horizontal. We then choose a uniform at that point between 0 and the red line, the majorizing function, which gives us a value of 1.05. Because it's above the PDF there of the beta, we will reject it. And so you'll see a red X appears. And so that one is not part of the sample. And so in this particular case, what we'll do here is the default is go until you have 10 samples. And every time you get a sample that's accepted, the histogram at the bottom updates itself. You can see that with only 10 samples, it's not a very good histogram representation of the underlying beta distribution. But for example, if Vadim were to up this to 50 samples and run them through quickly, you can see how it works here in these generation of 2 uniforms in trying to use this acceptance rejection approach. And so again, the green circles are things that were accepted, the red X's were things that were rejected, and the ones that were accepted are producing the histogram below, which looks a little better. And of course, again, natural sampling variability, and we can also talk about size of sample. It allows us to talk about lots of different things in simulation approaches. So that's the nice AR sample function. You can choose different PDFs if you want. You can choose different majorizing functions. We don't have time to show an example right now, but Vadim in the examples that are going to go in the R package has a nice piecewise majorizing function, so it squeezes a little more tightly toward that beta function. And so you can, as an instructor, you can really play around with this and talk about how many accepts there were and how many rejects there were and so forth. So that's the AR sample function. And then we've got time for one more to show you. And this was really I think the piece de resistance of the work that Vadim has done. And this is a visualization of a single server queue, but it's a bit novel in the sense that it is not just animating the queue itself. Instead, what it does is it gives a really nice animation and visualization of the event-driven approach. So when we talk in a simulation class, particularly I'm a computer scientist, what we'll often talk about is how do we build the details? How do we actually build that simulation? And I have my students implement it. Not they use it initially in R, but they also have to implement some of these things, whether it's in Python or Java or C++. So here's the basic idea. In a single server queue for an event-driven approach, we have what's known as a calendar, which will keep track of future events. As it turns out, for a single server queue, there are only two types of events in this simple thing. There's an arrival to the system, and there's a completion of service. So before we start up the simulation, what we have to do is we have to initialize the calendar. Just like your favorite coffee shop, you don't have a customer leave until a customer has arrived. So before we start, the first thing that can happen is an arrival has to occur. So what we're going to do is we're going to generate that first arrival. And so we do that by, this is similar to those I star functions we showed earlier. We're going to generate a uniform 0, 1. That's that little purplish dot on the left. And so then we will invert that back across the CDF corresponding to the arrival function. In this case, it's an exponential with rate 1. That gives us an inter-arrival time here of 2.054. When we add that to the current system clock, which is 0, that means our first arrival is going to occur at 2.054, shown in yellow. And so we'll put that into the calendar. And so once we've done that, we have initialized our calendar. And now we can essentially enter a while loop where we pick out the minimum time out of the calendar and then process the corresponding events. And so in this case, the minimum is going to be an arrival. So what you can see in the middle then, which is what you might see in a more traditional animation of a single server queue, what you have there in the middle is our queue with the server on the right, and jobs come in from the left, and customers come in from the left, and they leave out to the right. So in this case, we have that first job has just gone into the server. We're coloring it orange at this point because we still have to generate a service time for this one. So that's what's next in terms of handling this arrival. So we go back up into the generation thing at the top. We generate a uniform 0, 1 on the vertical. We map it back across the CDF corresponding to our service process, which in this case has rate of 1.11. And so the service time generated for this job is 0.4. So we add that to the current clock time to figure out when this particular customer is going to leave, which will be 2.455, and that gets put into the calendar. But before we can finish processing this arrival, we also have to say, when is the next job going to arrive? You can see it sitting down there in the middle. It needs time. Same kind of thing, generate a uniform 0, 1, invert it back across the inter-arrival CDF. We get an inter-arrival time of 1.05, add it to the system clock, and the next arrival will occur at 3.060. All right. That has processed the first arrival, and you can look in the middle there and see what we have is the first customer is sitting in service right now, where now we have the server colored green because it's active. And so that particular customer is going to leave at eventually time 2.455. So we just repeat this process of the while loop, simulating for some amount of time. And those are the details of the event-driven approach. But at the same time, students can see at the bottom there in row 2 and also in row 3. So row 2 shows what the queue looks like as things back up. So Vadim, jump ahead several jobs. Several customers. All right, and so what's going to happen here is Vadim is able to jump ahead. And so what we've done at this point is we are now where the 9th customer has just moved into service. There's currently no one in the queue, but you can see below in the 3rd row, there is some statistics, some what we call time persistent statistics. And so those curves right there show, for example, how many are in the system across time or how many are in the queue across time. Over to the right, we have individual statistics as well as some aggregated statistics. And so it's a really nice way for students to not only visualize the queue itself and the statistics, but also really see the guts of an event-driven approach. So jump ahead 10 more, Vadim, and let's see whether we can get some backup in the queue. All right, and so here's an example where the 17th customer is in service. Customers 18 and 19 had to wait in the queue. Customer 20 has not yet arrived, and then you can queue to jump to the end, Vadim. And so what this will show us is the final thing where in this case, we were processing only 40 customers. So you can see the 40th customer has left the queue, and what we have at the bottom then are the overall stats for the end. If you look out to the right, those are the individual, for example, number in the queue, number in the system, number in service or utilization, as well as individual statistics. And back to the left there, those are what we call the skyline function that we can use to compute time persistent statistics. For that black line, every time there's a jump up, that means there was an arrival to the system. Every time there's a drop down, that was a completion of service from the system. And so those are some really great visualization routines so jump back to the slides, Vadim, just to wrap up. So this is our Symud package. We currently have a version available on the CRAN that has mostly the text-based routines. All of these really nice visualizations that Vadim has developed as part of his summer and undergraduate research will be put on the CRAN soon. Please feel free to contact us with any questions or interest, in our email addresses are there. So thanks for your time.
Thank you all. That was amazing. We have a question with regards to the visualizations. What are you using to make these visualizations for the process arrival?
I'm going to leave that to Vadim.
Okay, so it's kind of interesting. If you're familiar with the Animate library, I believe it is, with Dr. Z, it's similar in its approach, but it's kind of a custom thing entirely. I was thinking about possibly putting that as an independent thing later, but as of right now, it's essentially just dev.hold, dev.flush, and sys.sleep, but in a interesting way, as in the actual, it does it lazily. So essentially the first time it just skips over and records the current plot, and then after that, it'll show what just happened earlier. So every time you click, it's responsive at that moment. If you're curious,
but for the most part, you're just using native drawing capabilities in R, right, Vadim?
Yes.
Except for the shape library, which allows us to have those pretty arrows.
Yeah, pretty arrows and circles in the shape library, but overall it's just some things from GR devices, and that's about it. If you are interested in learning more about that, feel free to ask. And also, if you're interested in trying to do that kind of thing in Shiny, feel free to ask as well.
Fantastic, thank you. And another question is, considering how this is an educational package, is there a corresponding syllabus for people to use on their own?
Oh, that's a good question. We don't have one as of, Larry and I would certainly be happy to share our own syllabi that we use. He and I teach a little bit different simulation courses because he's on the mathematics side, I'm on the computer science side. And so really what we are hoping for is that this can meet a lot of different needs, so that, like on my side, when I have students really get into the nitty-gritty implementation details, they do that later in the semester by using Symud up front to get some intuition. And if you have, perhaps in mathematics, where you don't want to have students doing so much implementation detail, they can live mostly in the Symud package and do some things related to that, along with all of the other capabilities that R provides for analyses.
And maybe I'll add to that, Barry. Barry and I are working on a book right now, and it's in draft form, but if somebody were interested in possibly using the book, which works in conjunction with the package, please contact us.
Fantastic. Thank you, Barry, Larry, and Vadim.
Thanks, Ben.
Thanks.